In this video, we're going to take a look at something called the integral test. It's the first of a bunch of what are called convergence tests, where we are going to look into different ways of determining whether a series converges to a given sum, or if it diverges off to plus or minus infinity, or alternates between values and never winds up converging to any values at all. The reason that we're doing this is ultimately, again, with the goal of building Taylor series in mind. We said that you can represent lots of functions using some sort of infinite series, but if that infinite series doesn't converge to anything, namely if it doesn't converge to the function that we're trying to approximate, then it doesn't do us any good. So basically, for the remaining sections, or probably for the next 4 or 5 sections, we're going to be looking at different types of convergence tests to determine whether or not a series converges. And the integral test is just the first of these. It turns out that, in general, finding the sum of a series is really, really hard. And I don't want to understate this. Finding the sum of a series is hard. We got lucky and we had a couple of cases with the telescoping series and with geometric series where there was a closed formula that can give us this sum. But for most series, there isn't, we aren't so lucky. There isn't a formula that's going to give us the sum that we're looking for. If we can find a formula for the nth partial sum, then we can use the approaches that we did back in 11.2. So if we can find a closed formula for the nth partial sum, which we were calling S sub n, then we can use the methods that we talked about. Right, we can see the limit as n goes to infinity and see if we can figure out what this sequence of values is going to do in that limit. Oftentimes, though, this isn't possible. And so let's look at an example. Consider the following. If I give us a series that looks like the following, I'm going to do the sum from n equals 1 to infinity of 1 over n squared. Right, so I have a closed form for the series. I can write down the a sub n's, the individual terms that go into the series. This thing looks like a 1 over 1 squared plus a 1 over 2 squared plus a 1 over 3 squared plus 1 over 4 squared, and so on and so forth. And if we actually evaluate these, it's 1 plus a 4th plus a 9th plus 1/16. And if we look at the sums, the corresponding sums, so if we look at the various SNs, the first one would be 1. Then the second one we'd add up the first 2 terms, so 1 1/4, which would be like 5 quarters. And then after that, we're going to have to add a 9th to this. The common denominator can be maybe 36, I guess. So we could do, geez Louise, how many 36ths is this? Is this 45 36ths? Did I do that right? 45 36ths plus 4 36ths. So this next one would be like 49 36ths. Then the next common denominator, we're going to have to factor in another factor of 4, so it'll be, I don't know, I guess 4 times this number, so I don't even know what the next one's going to be. I don't want to put a plus sign there and confuse things, but As we get the various sums of these, so 1 by itself is easy, 1 plus a quarter not hard, 1 plus a quarter plus a ninth gives us this, I think. If I add another 16th to that, we'd get some other number here. But there's not a clear pattern that's going to be emerging right here. There is no simple formula. For S sub n, for that nth partial sum. But there is something that we can do. Instead, let's look at a graph of a continuous function. What we can do is the following. I'm going to draw my axes here. So here's my x and my y axis. And I'm going to graph the function y equals 1 over x squared. So I'm going to do y equals 1 over x squared. We'll come back to exactly why we're doing this in a minute. But let me try to put some values on here and draw this semi to scale. So 1 over x squared is going to go through this point. We'll go through the point where the height is a fourth, then a ninth, then 1/16th, and it looks like this. And let's try to draw that a little more smoothly. Okay, so that's what this graph is, y equals 1 over x squared. And if I look at these rectangular areas underneath, I can figure out what the area of each one of these is. So what is this area? Well, its width is going from 0 to 1, and it's a rectangle, so it has a width of 1 and a height of also 1. So the area of this one is 1, assuming that that's our origin there. What is the area of this rectangle? The area of this rectangle, this area is going to be 1/4 because it has the same width of 1, but the height is now 1/4. So for all of them, the width is 1, and the height will determine the total area. This one has a height of 1/9. Because again, I'm plugging in the point. Where am I getting these heights? I'm getting the heights by plugging in the various points. The point 1, when I plug it in for x, the height is 1. When I plug in 2 for x, I'll get 1/4. When I plug in 3 for x, I'm going to get 1/9. And so that's what's giving me these values of the heights of the curve, which then correspond to the areas, because the width is always 1. So I can see what's happening to the areas here. One thing that hopefully makes this obvious to you is maybe I didn't know whether or not this original series converged, but by looking at this picture, if the integral converges, then so will the sum of all of these areas, right? The integral is the total area under the curve. And in this case, I'm adding up a bunch of rectangles where clearly there's some leftover area. So they're going to give me an area that's even less than whatever the integral is. So if the integral converges to some finite value, then certainly the sum of the areas of the rectangles will converge to some finite value. So if the integral of 1 over x squared converges, so will the series. In fact, really it's this first term that's the one that's kind of questionable. Looking at this portion of the graph after x equals 1, we can see that definitely the rectangles are much, much smaller, and we can get some bound on what the sort of an upper bound, if you will, to what the sum of the series will actually wind up being. It's really this piece up here, which again I don't have shaded in, but imagine we shade this one in, and just keep in mind it goes all the way up to infinity. This is the piece that I really don't know if it's going to converge or not. This is the piece that I probably should worry about. So I don't even need to worry about this piece. I definitely know that the area underneath it is finite. This rectangle is a 1 by 1 area of 1 finite area. So even if this area up here that's shaded winds up not being finite, if this winds up blowing up, I'll still have the rest of the integral converge as long as the area starting at this point over converges. So what I'm suggesting is basically even if we exclude that first term, if we exclude the first term, zoom out so we can actually get this all on the page at once. If we exclude the first term, the remaining terms must sum to less than the integral from 1 to infinity of 1 over x squared dx. And that means if I look at our series 1 plus a quarter plus a ninth plus 1/16 and so on, plus dot dot dot, that must be less than 1 plus the integral from 1 to infinity of 1 over x squared dx. And this integral is one that we can do, and it turns out that integral winds up being 1. It's an improper integral that we did back in previous parts of the semester. But that thing adds up to 1. So this whole thing, this sum over here, is less than 2. I don't know exactly what it is, but I have an upper bound. Can't be bigger than 2. Just real quickly, maybe as a side note, I'll do this over on the side. We can check this integral real quickly. So where did we get that value of 1? Again, it's an improper integral in this case because the bound is infinite. So I'm going to take the limit as c goes to infinity of the integral from 1 to c of 1 over x squared dx. We'll integrate that. I'll carry my limit down. The integral of 1 over x squared is negative 1 over x. You can think of it as an x to the negative 2 power. When you go up in power from negative 2, you'll go to a power of negative 1, and you'll need to pick up a negative sign to account for that when you take the derivative. So this is what the integral of this looks like, and we're evaluating it between 1 and c. And so we get the limit as c goes to infinity of negative 1 over c minus negative 1. When I plug in the lower bound of 1, I'll just get negative 1 over 1, which is our negative 1. Change that minus a negative to plus a positive. Take the limit as c goes to infinity, and that first term will go to 0. We get 0 plus 1, which is 1. And that's where this number came from here, where we got the value 1 for all of this. So just a quick reminder of how we approach these improper integrals where we have infinite bounds of integration. We just use limits. Okay, so again, I've got this sum. I don't know what it sums to, but I know it sums to something that's less than 2 because it's bounded by that integral. So that integral is the integral in our integral test. But now I want to consider another option. So instead, let's consider, so a minute ago we did this sum, the sum from 1 to infinity of 1 over n squared. Now I want to do the sum from 1 to infinity, so n equals 1 to infinity, of 1 over, let's do the square root of n. So in this case, this is going to be equal to 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 plus dot, 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 dot. So same idea as before. If we graph this one the same way, so again, there's not going to be a nice closed form for the nth partial sum of these, but if I graph it, what we get is a picture that looks something like this. Looks similar to the one that we drew a minute ago. So there's my x, 1, 2, 3, 4, height of 1. And here I want to graph y equals 1 over the square root of x. So when I plug in x equals 1, it'll go through the point 1, 1 right here-ish. When I plug in 2, it'll go over the point 1 over root 2. 1 over root 2, which is like root 2 over 2, is like 0.7-ish something, so still pretty high up here. 1 over root 3, so root 3 over 3, root 3 is like 1.7-ish. If we divide that by 3, we'll be down at like 0.6-ish, a little less. So it's going to be down here maybe. Same thing when I finally get to 1 over root 4. That's the same as a half. This will be down to a height of a half. And I'm doing the same thing we did before. I am hopefully kind of semi-smoothly drawing the curve that goes through all of those points. Let's see if I can get it any better than that. Good enough. So let's say those are the various heights there. And in this case, I could try to draw the areas underneath, and we could deal with that. But in this case, I'm going to draw the rectangles basically to the right. So on this drawing up here, I used essentially what we call the right endpoints in drawing my rectangles. So each interval, each rectangle that was drawn, the height of it was determined by the right endpoint on the curve. And that made them, in this case, go underneath. Over here, I want to use all the left endpoints. So this first one would be way off up at infinity. So I'm not even going to worry about it. It goes up to infinity. I have no idea what it's going to look like other than that my first rectangle is going to be big. So I'm not even going to worry about it. I'm going to instead worry about these rectangles. So here's the first rectangle that I want to look at. And then here's the next rectangle. And here's the next rectangle, and so on and so forth. They would look like that. What are the associated areas here? Well, again, I've designed the areas of these to line up with these numbers over here. What's the area of this first rectangle I've drawn? It has a width of 1 and a height of 1. So the area of this first one is 1. What's the area of the next one? Well, again, the width is 1. And the height is 1 over root 2 by design. That's what we designed this point right here to be a height of 1 over root 2. So this has an area of 1 over root 2. The next one has an area of 1 over root 3. The next one would have an area, which I didn't really leave room to draw in. Imagine that next one there would have an area of 1 over root 4. So in this case, our sum, we're going to compare it again to the integral from 1 off to infinity of this function. I know that the rectangles have a larger area than the integral of the curve, starting at 1. So in this case, we see that my sum, 1 plus 1 over root, plus 1 over root 2, plus 1 over root 3, plus 1 over root 4, plus dot, 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 is going to be larger than the integral from 1 to infinity of 1 over the square root of x dx. Because again, that's what this curve is. So again, I'm suggesting basically the area of the rectangles over here is now greater than the area under the curve. Right? Here's the area under the curve, which is clearly less than the sum of all those rectangles starting at this point, starting at 1. Okay, let me erase those just to have it easier to see. So now I just need to look at this integral. Well, it turns out that this integral diverges. It goes to infinity. It blows up. If this goes to infinity, if the integral goes to infinity, and the sum that I've got is greater than that integral, that must mean this sum must diverge. And we've actually looked at this. This is going to lead us to a really important point in just a minute. So I'm not going to necessarily go through. I guess we could. What the heck? We'll do it now. So again, just as a side note, just because I did this one earlier, we looked at the integral of this one and saw that it converges to 1. Let's take a look at this integral and see what happens. So what is this integral? Integral from 1 to infinity. So again, it's an improper integral. I'm going to do the limit as c goes to infinity of the integral from 1 to c of, I'm going to just write that as x to the -1/2 power dx. Right? 1 over the square root of x, that's x to the -1/2. So this is our integral. We'll compute that integral and keep our limit here for a moment. X to the -1/2, that'll give me a result of x to the +1/2. And we just need to make sure that we get the other factor correct in front of it. So again, if I were to take the derivative of x to the 1/2, the power would reduce by 1 and I'd get a -1/2 as my power, but I'd also bring a factor of 1/2 down in front that I don't have here. So I need a factor of 2 there. So this is now the integral of what we've got up there, and I just need to evaluate it between 1 and c. So this 2x to the 1/2 is the integral of x to the -1/2. We'll evaluate our c, so I'm going to get 2, we'll write this as square root of c minus 2 times the square root of 1. So, and, oops, I forgot my limit. We still need the limit there. The limit as c goes to infinity of 2 root c minus 2 root 1. And when we plug in that limit, we're going to basically get 2 times the square root of infinity minus 2. What is this thing doing? It's diverging. It's going to infinity. The square root of infinity is still infinity. So this whole thing diverges. Right? Plugging in an infinity here is kind of an abuse of notation a little bit, but the whole thing is diverging. It's blowing up. And that's how we know that this integral here diverges. Okay. So this is the idea. This idea leads to the integral test. And it basically says if we can come up with a curve, a continuous curve, that the heights on those curves at various discrete points match the values in our series that we're trying to add up. So basically, if I can find a way to tie the area or treat these numbers here as areas that we're adding up, and tie those rectangles to some curve that's a continuous curve, I can compare the area under the curve to the area of the rectangles. If I find an area under the curve, so the integral, if I find an integral that diverges, I need to make sure that my rectangles are larger than that area to ensure that they also diverge. Alternatively, if I find an integral that converges, so the area under the curve converges to a value, I need to make sure my rectangles fall under that curve to ensure that it also converges. So what I'm suggesting is, in this case, the integral converged. We just did the work for that over here. If I'd drawn my rectangles to be above instead of below the curve, I wouldn't have shown anything. It's kind of like the squeeze theorem from before. Basically, I know what if I know that the thing that is larger is converging to some finite value, then the thing that is smaller must also converge. Or alternatively, if I know the thing that is smaller is diverging off to infinity, then the sum that is larger must also go to infinity. So you've got to be careful about making sure that you have your integral relate correctly to your series. If you want to show that your series diverges, you need to ensure that the area of your series is larger than the integral that you're comparing it to. If you want to show that your series converges, then you need the areas associated with your series to be smaller or below the curve that you're using to show that that curve converges. So this integral test works basically whenever we have a continuous, positive, and decreasing function, f of x. So it works on continuous, positive, decreasing functions, f of x, as long as basically f of n is equal to a sub n. So basically, if you plug in the integer values for x, you get the associated terms in your series. So hopefully that makes some sense, but again, you've got to do it the correct way. If you're wanting to prove divergence, you need to make sure that your rectangles are larger than the integral that's diverging. If you want to prove convergence, you need to make sure that your rectangles are smaller than the area of the integral that is converging. So you've got to make sure you squeeze it on the correct side. But all of this leads us to a really important finding. This is probably going to be one of the most important things that we'll use when it comes to all of these convergence tests, and it's something called a p-series. So p-series is an important topic. The p-series looks like the following. The p-series is the following. The sum from n equals 1 to infinity of 1 over n to the p. So it's going to be equal to 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p plus ... And you'll see that both of the series that we just looked at fall into this form. So over here, the first one, let's go all the way back up. The first one was 1 over n to the power 2, so p was equal to 2 in this case, so 1 over n squared. That was one series. And then the second one we looked at right here was 1 over n to the 1/2 power. So the value of p in this case was 1/2. In general, it turns out that we can let p be any number that we want it to be, and this series is going to converge. So let me write it this way. Let's do bullet points still, but let me say it converges basically if p is greater than 1. So if this power is greater than 1, so for example, the one that we did up there, it was the first example, it was 1 over n squared, so the value of p was 2. We saw that that one converged. Turns out the cutoff is p equals 1. If p is greater than 1, it's going to converge. It diverges, if p is less than or equal to 1. And we're going to stick to values of p that are positive. So let me do this. 0 less than or equal to p less than or equal to 1. And let me not even do less than or equal to here. Let's just do strictly positive values of p. And again, we get this result in each case by comparing to an integral. And in general, the integral looks like the integral from 1 to infinity of 1 over x to the power p dx. This was discussed way back in section 7.8. When we talked about improper integrals. So it was way, way, way back there. We literally did this exact problem and looked at what are the values of p where this will converge, what are the values of p where this diverges. So I'm not going to redo it all again here. If you want to go back and review it, we did this problem way back in section 7.8. So that was a while back. But this is a really important idea. 1 over n to the p is our p series, basically, or the sum, rather, of 1 over n to the p is our p series. It's going to converge whenever p is greater than 1. It's going to diverge whenever p is less than or equal to 1. So, for example, if I asked what is this sum, I'm not even asking what is the sum. I'm simply asking, does it converge or diverge? If I did 1 over the cube root of n, in this case, that implies that p is equal to the power of 1/3. And that means that this thing diverges. If we did the sum from n equals 1 to infinity of 1 over, let's say, the square root of n cubed, well, in that case, that power of p there, we have a 1/2 from the square root. We have a 3 for it being cubed. P is equal to 3/2 in this case, which is greater than 1. So it converges. And so whenever you see something of this form, or you can compare to something of this form, you can immediately say, I know that this is either going to converge because p is greater than 1, or diverge because p is less than or equal to 1. So the p-series is going to be a really powerful tool that we're going to use a lot going forward. So just keep that in mind. One important thing that we're going to want to be able to do with this, so again, this should be super important, big circled idea. Well, let's try to make that a little better, less intrusive. But this whole idea, super important. That's going to be something that you want to just have down, that you want to have memorized. And we'll actually talk about this a little bit going forward. Again, we'll come back to this again and again and again. But one thing that we can use some of this for is estimating the remainder within one of these series, or the sum of one of these series. So this is something else I want to talk about. How do we estimate a remainder in a sum? What do I mean when I say the remainder? Generally, we're doing an nth partial sum, right? So maybe we're only adding up the first 3 terms, or the first 4 terms, or the first 5 terms. And the plus ... kind of represents all the remaining terms. Maybe we want to estimate how much is in that plus ... after we've cut it off. That's going to be an important idea as well. So if we look at the pictures that we had in our 2 different cases, I just want to kind of think about what that remainder is going to look like. So let's do this. Let's start with that first graph. I think that's going to be the slightly more informative one to look at here. So x, y, we get our curve. It looks something like this. and we had basically some cutoff after, let's say, hypothetically, however far we've gone into it, this is the value of n. So who knows how many terms it took to get here. Maybe this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or something like that. Who knows? It doesn't really matter, but the point is I just want to be able to figure out the remaining area after that point. So by the time I get to n plus 1 and n plus 2 and so on. So let's say here's where n plus 1 is. Here's where n plus 2 is. And here are those rectangles corresponding to these various pieces. N plus 3, n plus 4, dot, 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 dot. So basically, if we look at the areas of this, this will have an area that will associate, if we come back up to our first picture, just to remind you what we were doing. This was the first term. It was associated with the value n equals 1. So basically the area that we were interested in was the area to the left of the value of n that we were interested in this case. So over here, this was our first area, our second area, our third area, our fourth area, and so on. So the area was always to the left of the particular value of n that we were interested in. Same thing is going on right here. So that means that this area is the area associated with n plus 1. Here's a n plus 1. Here's the area associated with n plus 2. Here's the area associated with n plus 3. Here's the area associated with n plus 4, and so on. If we think about how this is going to work, the assumption is we've already accounted for all of the sum to the left of this. So here's the sum. Here's the partial sum. S sub n. Granted, it's going to look like, again, a series of a bunch of rectangles, whatever it happens to look like. But basically, everything to the left of n is stuff that's already been included in our partial sum, S sub n. And the remainder is anything that comes after n, so all of these areas to the right. And then we also have the total sum, where if I include all of the values on this side, plus all the values on this side, infinitely going on forever, we'll arrive at our full total sum. And out here again, this is just our y equals f of x, our decreasing positive continuous function. So, and these make up the remainder, which we're going to call r sub n, the remainder of everything that comes after n. So S sub n is everything to the left of here, the sum, the nth partial sum, the sum of all the terms that were up to n. The remainder, which we're going to call r sub n, is the sum of all the remaining terms that comes after we get to this nth position on the graph. And then the actual sum if you'll recall our notation, if we sum from n equals 1 to infinity of all the terms, we called that S. It is also the limit as n goes to infinity of S sub n. So, what we get is the following. We're going to get that the remainder, r sub n, is going to be equal to, so the sum of all of these terms is going to be the sum of all of the terms, S, minus the terms that occurred to the left. So it's going to be S minus S sub n. So what I'm suggesting is, let me do some colors here. One way to think about it is if you sum up all the red ones, that is this term, with all of these, and again, I apologize if anybody's colorblind. Here's all the blue terms, that is this one. You would get basically that S sub n plus R sub n must add up to the total S. And I've just rearranged this by subtracting S sub n from both sides to get R sub n equals S minus S sub n. And so that's what we've got right here. I'm taking the total sum, which is the area of everything. It's what you get when you add the red rectangles to the blue rectangles. We get S. The red rectangles to the blue rectangles. We get the total sum, and then I've just rearranged that sum a little bit here. So this is going to be the approximation for the area of area A sub n plus 1 plus a n plus 2 plus a n plus 3 plus dot, 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 dot. These are the areas that we just described right here to the right of n. So looking at this picture, I now have an upper bound for what the area of these blue rectangles should be. This is sort of the idea of what it is exactly, where S is going to this sum. But if I compare it to the smooth curve, I know that the remainder, the area of the blue rectangles, must be less than the area associated with the smooth curve, which I could just simply call the integral, basically starting at this point n and going up to infinity. So what's important here is I have a bound for what this remainder is going to be. The remainder, you'll recall, is the area of the blue rectangles, and I know the area of the blue rectangles is less than the integral for starting at this point n and going off to infinity of our y equals f of x curve. And so now I want to draw another picture. I want to have the same curve, but I need to draw another picture a little bit more carefully this time to get another bound. So again, I have an upper bound on that. Now I want to get a lower bound. So let me draw the same curve. Here's our hypothetical. Let me just make sure I make it look vaguely similar. Assume this is the exact same curve. So again, this is y equals f of x. And here's our point n right here. What I want to do here is come up with another approximation. So let me plug in some of the adjacent points. Here's going to be n plus 1, n plus 2, n plus 3, n plus 4, and so on. The same points that I've got drawn right here. Got them drawn again over here. So before, we drew all of these rectangles like this underneath the curve. All I'm going to do now is shift every single one of these rectangles over to the right. So I'm still going to have the same picture of rectangles, but they're going to change where they get drawn relative to the curve. So basically, what I'm saying is up in the first picture, I used the right endpoint to draw a rectangle. But now I want to use the left endpoint to draw a rectangle. So now I want to use this to be that first rectangle, then this, and so on and so forth. This height of the curve is still the height at n plus 1. That matches the height right here at n plus 1. So this height of this point right here, there's our height at n plus 1. This is still that same point. This is the height at n plus 1. But now I'm looking at, instead of drawing a rectangle to the left, I want to draw that rectangle going to the right. And what this means is, what is the area of this first rectangle right here? This is the area an plus 1. This is the area an plus 2. This is the area an plus 3. This is the area an plus 4. And notice I have a gap here. I'm leaving off this first piece that up here, if I draw see these pictures side by side, They're not quite drawn to scale. I didn't draw them quite as similar as I might have. But notice that basically over here, we started the blue rectangles at n. This area had a width of 1 and a height of whatever the value is at n plus 1. So what we're calling an plus 1. Same thing here. The width of this first rectangle is 1, from n plus 1 to n plus 2, and its height is whatever the height is at n plus 1. Height at n plus 1. All I've done is basically take every single one of these rectangles up here and shifted them to the right. And by shifting them one over to the right, now instead of being under the curve, now they're on top of the curve. And that's the same set of rectangles. So this set of blue rectangles exactly matches this set of blue rectangles. In this picture, we see that the sum of the areas of the rectangles is less than the curve from n to infinity if we do that integral. Over here, I'm saying that now the sum of those exact same rectangles that have just been shifted to a new position is going to be greater than the area under the curve starting at n plus 1. So over here, we were comparing it to the area of the curve starting at n. Down here, we're comparing it to the area of the curve starting at n plus 1. So from the pictures, if we start comparing the pictures, I'm going to get two estimations. I know the first one says that or in this case, yeah, so let's do both of these. We've got, in this top case, the remainder, the sum of the blue areas, is less than the integral starting at n going to infinity of our f of x function. So it's less than the integral from n to infinity of f of x dx. This is from the first picture. And the second picture tells me that I also know that r sub n is greater than or equal to the integral from n plus 1 to infinity of f of x dx. Now I'm just comparing it to the curve starting at this point. The sum of the rectangles is greater than the integral starting right here. And the only difference is now we're starting at n plus 1 for our lower bound, whereas up here we were starting at n for our lower bound of integration. So I have that r sub n has to be smaller than this, has to be greater than this from our second picture. So I have both an upper and a lower bound. So we get from this the following. If our function, f of x, if I evaluate it at a point k, and we call that a sub k, the height of the curve, where f has those conditions, it is continuous, it is positive, but it is also decreasing. So f is continuous, positive, decreasing function, at least for all x after a certain point, after n, the point that we're interested in. And if the sum of all those values of a is convergent, so assuming it converges, and if we define our r sub n as being the total sum minus the nth partial sum, then we have bounds on this r sub n. We know that the r sub n is between the integral from m plus 1 to infinity of f of x dx, and it's less than the integral from n to infinity of f of x dx. It's bounded by those two integrals. just based on taking the picture and shifting it over a little bit. So if we try to rearrange to try to predict what the total value of S is, right, which is ultimately typically what we want. Right now we're talking about this remaining piece, and we're comparing it to the nth partial sum, and we're really interested in the total sum. If I wanted to solve for S instead, we just need to add S sub n to both sides. So rearranging to solve for S, which is the actual true sum, we would get that S, which is equal to R sub n plus S sub n, has the following properties. We would say that S sub n plus this integral has to be less than or equal to the true sum, has to be less than or equal to S sub n plus the other integral. So integral from n to infinity of f of x dx. We can get a lower and upper bound on the total sum S. This is what we want. If you've taken n partial sums so far, we can figure out what the true sum is because we have some bounds on what the remaining portion can look like. So this is really a useful way of approximating S. We can do so to within a certain amount of error. And how big is that error? That error is basically our remainder, right? This is the idea. I think S is going to be approximated by S sub n by adding up the first n terms, and there's going to be some error involved. The error is whatever the remainder is. But because we now have bounds on the remainder, I can figure out overall bounds for S. I will know that it's between S sub n plus this small amount, and it's got to be, so it's got to be greater than S sub n plus this amount, less than S sub n plus this amount. We have bounds on exactly how big or small S sub S can actually be. Okay, so again, you'll get a few problems where you can kind of play with this idea a little bit. I don't want to dwell on it too much. Estimating remainders will be something that maybe comes up again kind of briefly down the line, but really I want the focus to be on this right here, the p-series. This is something that we definitely need for the whole rest of the semester, so we're definitely going to want to keep that. Let me toss in maybe just one or two more examples, and we can take a look at a couple of examples that will just help you on your homework. So in this first example, let's say that maybe the series we're looking at is the following. It's 1 plus an 8th plus 1 27th plus 1 64th plus 1 125th plus dot, 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 dot. I want to rewrite this as a sum of a bunch of terms. So can we figure out a way to put it in the form where we're summing from n equals 1 to infinity of some stuff? What are our a sub n's, the individual terms? And we'll notice this first term is just 1. The next one is 1/8, 1/27th. What I notice about the denominators here, and if I rewrite, especially if I rewrite this first one as 1 over 1, the denominators are all perfect cubes. Right? This is 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, 1 over 4 cubed, 1 over 5 cubed, and so on. And so it looks like this turns out to just be 1 over n cubed. As soon as we've got this, this is a p-series with p equals 3. the power here is equal to 3. So this converges by the p-series test with p equals 3. As long as p is greater than 1, this thing will converge. So I should have said that at the beginning. The whole thing I'm trying to do is decide, does this converge or diverge? So converge or diverge. And I want to ask that same question here. Let me even give you the sum this time. Let's write it out explicitly. I want the sum from, let's do n equals 2 to infinity of 1 over x ln x. So what is this? Is it going to converge or diverge? Well, as long as this thing can, and I did x ln x, and I meant to write, oops, let me erase it this way, n natural log of n. That's how this should have been written, right? There was no x in this problem. Same idea though. I want to know if this diverges or converges. Well, we can compare it to the function that I did write, 1 over x ln x, which is a continuous function, and that function is positive and decreasing as long as n is greater than 2. So 1 over x log x is positive. It's continuous, and it's decreasing for n, or x rather in this case, x greater than 2, certainly, which is the only region that we care about. Basically, I have a fraction, 1 over this number. If this number gets larger as x increases, then the overall number will be decreasing. And so x is increasing, log of x is also increasing, their product will certainly be increasing as well. And we can also verify that something is decreasing. One way to check for this is check the derivative and see if it's negative. If the derivative is always negative, then you know this thing is decreasing. So that would be another approach. But in this case, this increases, both things in the denominator increase as x increases. So the overall thing, whenever the denominator gets larger, the overall number must be getting smaller. So it must be decreasing. So I've got all of these met. We can apply the integral test to this. So this applies to the integral test, or rather I should say the other way around. The integral test applies to this. The integral test applies. Basically, what I'm suggesting is whatever the behavior is of this function, if this increases, or sorry, if this converges or diverges, that will match the behavior of this. So if we take the integral of this and see if it converges or diverges, that behavior will match the behavior of the whole thing. So what I'm interested in is the integral from 2 to infinity of 1 over x log x dx. So that's what we need. This looks a little bit tricky, but one way to think about it is the integral from 2 to infinity of 1 over the log of x times 1 over x dx. And if I recognize that I have both a log of x that shows up and the derivative of log of x, which is 1 over x, I can treat this as a u, and this is my du sitting right here. So if I let u be equal to the log of x, zoom in a little, whoa, a little too much. If u is equal to the log of x, then du is equal to 1 over x dx. And so I've got my du, and over here I have 1 over u. And I'm going to just do the integration, then I'm not going to bother changing the bounds. The bounds can always get a little finicky when you've got a bound of infinity and you're trying to plug into here. I'm not going to worry about that for now. So I'm going to keep the bounds in terms of x, and we'll convert back to x after we're done with our integration. So I want to rewrite this again as the integral from x equals 2 to x equals infinity of 1 over u du. And what is that integral? What's the integral of 1 over u? Well, that is going to be the natural log of the absolute value of u. And again, we're evaluating between x equals 2 and x equals infinity. And so we're going to have to, again, I've kind of been cheating. I should have written in my limit this whole time. Guess I can do that here. So let's come back and cheat. I'll just call this c, and put the limit as c goes to infinity. Limit as c goes to infinity. But hopefully you can tell by the way that I'm treating this as an afterthought that it is, as far as the computation is concerned, it is an afterthought, even if it is conceptually an important thing, that we need to be careful when we're treating these limits on these improper integrals. We do need the limit. And so let me come back over here. This one as well needs to be, oops, this whole thing, I need my limit as c goes to infinity, and this is x equals c. And so again, I need to just plug in over the region that we're interested in, which is starting at x equals 2. The log of x is always positive anyways, so I really just have the natural log of x evaluated between 2 and c, and again, we're taking the limit as c goes to infinity. Okay, finally. So now we can actually evaluate that. So I'm going to have the log of c minus the log of 2, and we're taking the limit as c goes to infinity. And what do we get from this? Well, the log of 2, this is just going to be some constant. Don't even care what it is, but it's some constant. And what about this? Does this converge or does this go to infinity? Well, as c goes to infinity, the log of c is also going to infinity, and the log of that infinity will also go to infinity. So this piece is going to diverge. This piece goes to a constant. And so if I have something that's diverging minus a constant, something that's going to infinity minus a constant, the whole thing is diverging. So in this case, coming back up here is what we've got right here, 1 over n log n. Is this thing going to converge or diverge when we take this series? And the answer is this whole thing diverges by the integral test. So the sum from n equals 2 to infinity of 1 over n log of n diverges by the integral test. And again, the integral test is just, can you find a continuous function that matches the terms you're going to get when you just plug in the integer values of x? So typically it's just replace the n's with the x's, and that is going to be your continuous function. And as long as it is positive, continuous, and decreasing, the integral test will apply.